Sorry for the interruption in the last video, but it was basically already finished. I probably would have just had one or two more words to say. I had a phone call that cut the video off. So in this video, we're going to talk about chapter 15, section 4. What happens when air rises or sinks. So we can start off with the scenario. As we learned from the previous chapter, as solar energy hits the Earth warms up the surface, and the surface provides sensible heat to the bottom of the atmosphere. So there's a parcel of air near the surface that gets warmed up. Associated with that increase in temperature, if that increase in temperature allows for the air to start rising, if that air starts to rise, that parcel of air will be associated with several changes. A decrease in pressure. This should be an obvious thing because we've talked about how the higher you go in Earth's atmosphere, the less air pressure there is. So same thing with this parcel of air. It's under more pressure close to the surface, and as that parcel of air rises, the pressures decrease. There's an increase in volume and a decrease in temperature. And we can plot those properties on a graph. And we can plot height above the Earth's surface versus temperature. And notice that the line has a negative slope. That is because temperature decreases with height. And we can calculate how much a rising parcel of air decreases in temperature and relate that as what is called the lapse rate. So basically the steepness of this slope is the lapse rate, and it is expressed commonly in degrees Celsius per kilometer, but you can use different units. And this is basically controlled by several factors: the temperature of the upper atmosphere versus the lower atmosphere, the temperature at which we started, and this constant lapse rate is called the adiabatic. Is called the adiabatic lapse rate. Now, this is the scenario if the rising air does not become saturated in H2O. Remember in the last video, if we're decreasing in temperature, eventually, if there's any water vapor, which there is in the atmosphere, if whatever vapor pressure is present can eventually become saturated, particularly if vapor pressure stays the same. So this has a couple important implications. The first of which, the saturation of air with respect to vapor pressure means that water vapor is going to condense. We're going to go from a gas to a liquid. And that process is associated with the latent heat of vaporization from the last chapter, or maybe 2 chapters ago. The conversion of gas to liquid, because gas is higher energy and liquid is lower energy, means that energy is released to the environment, aka surrounding air heats up. So that has implications with respect to the lapse rates. If we were to compare unsaturated the unsaturated lapse rate, the saturated the saturated lapse rate will be different. Now, since this is height and temperature, but we express it as degrees Celsius per kilometer, let me flip pins here. This is actually, even though on the graph it looks shallower, this is actually something that would be referred to as a steep lapse rate, because there's a lot of change in temperature versus height, and this is a gentle lapse rate because there's very little change in temperature with respect to height. So there are different scenarios, just to bring that back again. We could talk about a steep lapse rate, a moderate lapse rate, a very gentle lapse rate. The line actually plots close to vertical, or a negative lapse rate. So in this case, high change in temperature versus change in height. Change in temperature versus change in height. There's a moderate change in temperature versus a change in height. There's very little change in temperature versus change in height. And in this case, there's it's kind of confusing with respect to what I'm about to say. There's a negative. I don't want to use that word either, although it's kind of true. Introducing a double negative. Let's just say that this is a increase in temperature versus change in height. So we have a steep, moderate, gentle, and negative lapse rate. A negative lapse rate is associated with an increase in temperature versus a change in height. This is a special scenario that we'll talk about whenever we talk about weather. But to finish off this section, chapter 15, section 4, let's actually put all of this together and talk about stability, stable air masses. okay? Let's plot out everything that we have. Temperature and height. And just like in the book, let's give ourselves an unsaturated lapse rate. Let's give ourselves a saturated. Lapse rate, and call this field unstable specifically there, and then this should still be positive, so we'll do it right there, and call this stable and conditional. Conditionally stable. All right. So let's talk about these. Let's talk about this first. Let's look at this lapse rate. So this represents a very gentle rising air mass that cools relatively slowly with respect to height. This rising air is going to be cooler than the surrounding environment. And because it's cooler, cool air is more dense, so it's going to be less likely to continue to rise. And so it's preferentially not rising in this case, which is what makes it stable. In this scenario, we have a rising air mass that is much warmer at any given change in height compared to unsaturated air. And because it remains much warmer than the unsaturated adiabatic lapse rate, it's going to it's going to be encouraged to continue to rise. So because it's warm and because that property is encouraging it to rise, rising air is considered unstable, whereas stationary air, non-rising air, is considered stable. Within this scenario, specifically along this green dashed line, the reason it's conditionally stable has everything to do with respect to whether or not the air is saturated or unsaturated with respect to water vapor. If this rising air is unsaturated, it's going to be stable because it's going to be cooler than the surrounding air mass, and so it's not going to want to rise. But if water vapor is present or introduced, it's going to be unstable with respect to the saturated lapse rate. And so within any parcel of air that would plot its lapse rate between the unsaturated and the saturated is going to be dependent on the amount of water vapor that is present within the rising parcel of air, and whether there's more or there's an addition or a subtraction of that water vapor.